Hello, people. Welcome to the course Intermediate DSA. We'll be quickly starting with this course. The targeted audience for this course is people who wanted to learn, you know, DSA, advanced DSA. They have to must take this intermediate DSA course. Prerequisites: you should have basics of, some programming language like Java, good to have, or any other programming language. But you should have the basics. Let's say you should be able to write some for loop or while loop and understand the operators or keywords in the programming language. Number of modules, I am trying to keep it crisp and clear, so I am trying to do it in 12 modules. Suggested time, I mean, based on your availability and understanding, but you can actually go through this course and go deeper, learn some concepts, do some problems. I would suggest you can go for some 1 month, but we won't cover for entire 1 month. We will only cover 12 modules. To get started with, once again, welcome to the course. If you really wanted to learn advanced concepts in DSA and you are lacking some intermediate basics, you know how to write a while loop, how to use arrays, but you really wanted to learn graphs, heaps, trees, all that. For all those advanced concepts or algorithms, this course is must. So topics or modules, I am trying to keep it in 12 modules. We'll start with something with introduction to problem solving. We will also lay foundation stone for how do you compare algorithms in this, and we'll quickly jump into the time complexity. We'll see introduction to arrays. If you are new to arrays, it's okay. We'll see what is prefix sum. We'll see some techniques like carry forward or sliding window. We'll also cover memory management, sorting basics even. We'll also see 2D matrices, bit manipulation basics. We'll also cover string basics, and we'll see some interview problems. We have dedicated module for interview problems, but you need not to wait for module 12. As soon as you see some concepts you are learning, please go to some coding platforms like LeetCode, or Geeks for Geeks or any other coding platform. Solve some questions and try properly understanding the question. See, so far you might have learned programming languages, DSA in your college, but this time spend some time, actually understand the basics before starting advanced DSA. So I'm trying to keep this crisp and clear for you. We'll start with module 1 for today. In module 1, we'll discuss introduction to problem solving, where we'll start with counting the number of factors. We'll see what is a prime number, how do you relate this to factors. We'll see sum of natural numbers. We'll see definition of arithmetic progression and geometric progression, and we'll also see how do you actually find the number of iterations, or how do you actually compare two algorithms. Let me quickly start into our first topic for the day, factor, or counting the factors. Okay, straight question for you all. When do you say a number is a factor for another number? Yes, you are right. Whenever it divides. So, if A divides, n, then A is a factor, right? Now, I wanted to know how many such factors are existing for n. There won't be only one factor, right? There will be always greater than one factor. So if I take n equal to 24, now generally how do you find factors? If you ask me, in our basic mathematics we do, factorization, right? Prime factorization, or we'll find all the numbers. Simply to say, I am starting from 1, 0 cannot be a factor, 2, so on, and see which number actually divides n. So 1 is dividing 24, 2 divides, 3 divides, 4 divides, 5 no, 6 divides, 7 no, 8 divides, and if you compare, it repeats on itself. If 6 and 4 are there, 3 and 8 are there, 2 and 12 will be there, and 24 is there. So what is the flow generally I wanted to follow, at least for today? We will see the basic approach and we'll draw. So we'll see the approach, we draw some observations. As soon as we are drawing some observation, we'll do optimization. So which step is most important in this? Your approach and observations are most important, because if you have these two, your optimization is always green. You can always optimize your code. Observations are must, drawing conclusions is must. So from the above way, whatever I am discussing, right? If you try to put this in terms of a code, which is a brute force approach, right? Brute force or BF, generally you need the count. So count equal to 0, right? So what are we doing? We are iterating from I equal to 1 to n, right? Where we see if it is a factor, that number is properly divisible by the number a or I. If it is divisible by I, then what I am doing? I am increasing the count. Plus plus means one. Another way of writing this is count equal to count plus 1. So previous count plus 1. Okay. So once I do this, I am returning my count out of the for loop. These are must. I am clearly mentioning. Okay. Right. This is my brute force algorithm or brute force approach. I'll save this space for for optimizations to come in. Yeah, first approach is done, right? Yeah, very good. We did approaches. We'll see what are the observations we can draw, right? Before actually getting into observation, how do you judge any algorithm, or how do you say we can have some more optimized version of this? How do you say this is optimized or not? Time complexity? Yeah, but we'll get into that in next module. At least for now, if you stick to the basics of computer science, we will see execution time. Execution time. The time computer or a system takes, machine time to execute any program. So it depends on, let a computer is doing 10 power 4 iterations per second. That means consider this as a clock speed, frequency or clock speed of a computer. Now this is what I know about the computer, and I wanted to find the execution time. So to find execution time, you have to focus on how big the number is. Then you have to see how many iterations your code is going through, and you do the execution time for that program. Let's take an example here. If my number is 10 power 4, how many iterations the above approach will take? It is actually running from 1 to n, not skipping anything, right? In inside loop also I don't see any skip to anything, right? That means here it is doing 10 power 4 iterations only. So whatever the n, it is doing those many iterations, right? But the execution time is iterations by fixed clock speed or iterations per second. So it is 10 power 4 by what is the iteration of my machine? Iteration per second computer is 10 power 4, which is actually 1 second, right? If the number is 10 power 4. If the number is, some 10 power 5, my iterations again it is 10 power 5. So execution time is 10 power 5 by 10 power 4, right? This is the fixed clock speed and how many iterations it is running, that is 10 seconds. So far so good. But let's say my number is very huge. If it is 10 power 14, iterations are 10 power 14. In that case, 10 power 14 by 10 power 4 clock speed, which is equal to 10 power 10 seconds. Come on, take your calculators and tell me how much time will it take. Yeah, you don't need to do that. It's actually take somewhere around 327 years. So if you wanted to find the factors, number of factors for a number which is 10 power 14, you need to actually wait till 327 years, which is not possible. So I need to see how can I reduce my execution time. I cannot change every system, right? I cannot change the clock speed. And no matter how much you change the clock speed, you have a technology constraint, right? Then from this whole, I can only see how can I reduce my iterations. And that makes sense because 24 is only having 8 factors out of 24 numbers, right? So we can actually look for optimizing our iterations. To do that, let's draw some observations. Okay. How do I make observations? Let's take n equal to 24 only. I would say let's write all the factors. 1, 2, 3, 4, 6, 8, 12, 24. If A is a factor, you see 24 is also a factor. That means n by A is also a factor. So 1 into 24, 2 into 12, 3 into 8, 4 into 6, 6 into 4, 8 into 3, 12 into 2, 24 into 1. So first observation is, if A is factor, then n by A is also factor. Can I say they are pairs? Right. And what is the second observation? As A is increasing, right, n by A is decreasing, right? So as A is increasing, n by A is decreasing. So that means after certain point, right, factors started repeating until or after. After what? If you compare LHS with this number, after A is less than n by A, factors started repeating themselves, right? So can I consider this? So out of this, A square is less than n, or A is less than square root of n. So which means you don't need to check all the numbers. You can check numbers that is equal to or less than of square root of n. This is the observation we have made out of our basic approach. Now we can optimize the code, right? Instead of actually running till all the numbers, I will only run till a number which is less than or equal to square root of n. So my optimized code, would be, so I would consider optimization 1. I'm not sure, there will be many optimizations. So count equal to 0, for I is starting from 1 to, now it is only square root of n. less than or equal to square root of n, right? Less than or equal to square root of n. So again, if n is a factor of I is a factor of n which divides absolutely, then you can increase the count to 2, not 1, because the observation we made is they always occur in pair. So if you are considering 1, you should consider 24. If you are considering 2, you should consider 12, right? So I am doing plus 2, not plus 1, right? Yeah, there is no else after this return count. Cool. I mean, we have achieved, lot. We have eliminated lot of unnecessary iterations, right? But is there any scope for next observation? Do you think the logic fails anywhere? So for next observation, you have to clearly see what is the mathematical thing you have got here. You are talking something about square root. So you have to check this with any perfect square number. Okay. N equal to 100, which is a perfect square. Okay. That means 10 into 10. Right. It has a proper natural number as a square root. If you see the factors of this, it is 1. Right. 100, 250. 3 is not possible. 425. 520. 10, 10, 25, again 25, 4, 52, and 101. If you see this, yeah, pair exists, pair exists, pair exists, pair exists. Pair exists, but it is repeating itself. So ideally you will do comparison still here. So what happens? 2 plus 2 plus 2 plus 2 plus 2. You got 10 as a count, but actually there are 9 factors. You are counting 10 two times. So one edge case scenario we are missing. If it is a perfect square, the other pair is the same number, right? So still there is an optimization. Agree? So I'll complete that optimization. You put count equal to 0 first, right? For I equal to 1, I less than or equal to square root of n, or I plus plus f n divided by I. First of all, let's check whether it is a factor or not, right? Again, if I equal to n divided by I, that means both factors are equal. It's a perfect square if you get something like that. Then do count plus plus, not count plus 2. Okay. Else it's a factor and you are checking within the square root terms, within the square of a number, you have to do count plus equal to 2 and return your count. Let me write it properly. Right. Return count. Right. Clear. Now, as I said, we can look for execution time. Let's go for the same approach. Let's try finding the execution time. So now what happens? Your n is a number, but your iterations you are actually going till square root of n only, and we find the execution time. Okay. Computer is having 10 power 4 iterations per second clock speed. So same numbers will take 10 power 4, 10 power 5 and 10 power 14. So iterations are till square root of n only. So this is square root of 10 power 4 is 10 square. And the execution time would be 10 square by 10 power 4 clock speed. 10 power 4 is your clock speed, right? So it is 10 power minus 2. This is 0.01 second. So 100 times the execution time got reduced. Earlier if you check, it is 1 second, now it is 0.01 second. Now square root of 10 power 5, which is root 10 into root square. Again this is root 10 into 10 square by 10 power 4, which is root 10 is 3.14 into 0.01, which is 0.03 seconds approximately. Now it is 10 power 14 under root, which is 10 power 7. So 10 power 7 by 10 power 4, which is equal to 1000 seconds, which is much less than 327 years. Did we achieve the execution time? Yes, we have did it. So yeah, this is one example I wanted to show. We don't do every, we won't explain everything in such same manner. Since it's a first concept, I am telling you what is the importance of execution time and how do you find the approach, make observations and optimize the code. Yeah, let's quickly jump on to the next topic, and from now the topics will be really fast, which is prime number. When do you say a number is a prime number? If it is divided by one end itself, that means number of factors equal to 2. Now if a number has count of factors as 2, that's a prime number. So I'm giving a pause here. You can go through the video or pause the video, go back to count of factors we used and see, can you write a brute force or can you write an code first of all. Yeah, so I'm writing the code. I wanted to know if it is a prime or not for a given int n. What I do, I need a count first, then I use the count of factors method, which I pass in. What is this count of factors? This is the same logic whatever we implemented. You can use the optimization too in that method, right? So this will give me the count of factors. Simple. If if the count is equal to 2, return true, that's it, or else return, or you don't need else also. Actually you can write return false. By default, if nothing is there, this method will return false, right? That's it about prime numbers. We will see the concept of sum of n terms, and we'll see what is iteration and all. Let me talk about some other concept called range. What is range? Range means it's a series of numbers. Some numbers you include or exclude, right? There are two notations in mathematics. One is square brackets, one is open brackets. Square brackets means include corners. Open bracket means exclude corners. If I write something like 1 to square brackets of 1 to 11, that means 1 2 3 4 dash 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 11. If I write something like 3 to 10, which means 3 4 5 6 dash 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 10. If you see, 1 is included, 11 is included, 3 is included, 10 is included. And if I take the count, the number of count here, it is 11. Here the count is 8. So here I know I am actually having very finite set of numbers, so I can compare. But what if you don't want to count each and every number? How do you get this count? Any observation I can make? Since it's a sequence of numbers, right? You are right. Difference. Let's take 10 minus 3. This is 7, but there are 8 because you are including 3 also. So plus 1. Similarly, I can make the same observation for 11 and 1. plus 1, which is 11, right? So my observation is, if A and B is a range where you include A and B, the observation is B minus A plus 1. This is a generalized formula. But if I include A and exclude B, okay, so you can take always B minus A, then exclude B specially, so remove it, so it will be B minus A. Similarly, exclude A, include B would be something like B minus A plus 1, and you are excluding one number, that is A, it is always B minus A. And if you want to exclude both A and B, then you take A minus B inclusivity minus 1, which is B minus A minus 1. So this is the range I am talking about. Now, why do we need this range? If you wanted to see iterations of a loop, you should know what range it is covering. We'll take one example. For I starts from 1 to n, okay, if I equal to n, okay, then break. Come on. How many iterations do you think this will have? So it is going from 1 to n. For each I, it is checking with n. If it is I equal to n, it will break, right? That means n iterations, right? So you are including 1 and n. You can check it with B minus A plus 1, n minus 1 plus 1, which is n. We'll take one more simple example, okay? For I equal to 0 to 100, and I have some S operation, S equal to S plus I into I. Okay. What do you think? Or do you think the number of iterations here? I am giving a pause. Yes, you are right. It's 101. Because if you say I am not affecting I, or I am not breaking with any condition, so it obviously runs through 1 to 100. That means 100 and 1 are included, right? So 100 minus 0 plus 1, which is 101. Right? Clear? We'll take one more example. Okay, there is a function which has for loop of I 1 to n. Okay, it does some operation, and for loop of I 1 to n, it does some operation. So total number of iterations would be, since this is a sequence, one after one the for loop will run, this is this is n, okay, plus this is m, so m plus n iterations. Okay, there is a homework I would give you, try this out. Okay, let's say for I starting from 1 to n, right, if I star I is equal to n, then break. Okay, then find the number of iterations. Do this, let me know in the comment section. Okay, cool. This is clear, right? Now we'll cover a few fundamentals of sequence numbers in the same flow. We'll see sum of natural numbers. We'll see this, and we'll see AP and GP, but we won't derive everything, but we'll derive this one. So there is a story. A teacher asked a student to add numbers from 1 to 100 because he's making lot of noise in the class. What that kid has did, he made an observation. He took 1, 2, 3, 4 to 100. So I'm taking sum of natural numbers 1 to 100. Right? He reversed it and started adding the numbers. He did this because he observed 1 plus 100 is 101. In the same way, 2 plus 99 is observed. So how many times this 101 is coming? 100 times. This is x plus s is 2s. So s is equal to, can I write 101 into 100 times by 2? Right? It's a first n 100 natural numbers. So what is the observation he made? For n natural numbers, right? Sum equal to n into n plus 1 by 2. This is the observation he has made. Right? This is very important. This is an observation he has made. Now we'll see arithmetic progressions. What is arithmetic progression? A series in which difference between consecutive terms is constant. Example 2, 4, 6, 8, 10. Right? The difference, if you see, plus 2, plus 2, plus 2, plus 2. Or it can be sometimes 3, 1, minus 1, minus 3, minus 3. If you see here, it's minus 2, it's minus 2, it's minus 2, it's minus 2. So I can always say there would be a starting term and there would be a common difference. Right? So the nth term is given by the formula a plus n minus 1 into d, or the sum it is given by sum of first n terms in arithmetic progression is n by 2, 2a plus n minus 1 into d. These are must for arithmetic progression. You can take an example. Let's take minus 3. Minus 3 is a fourth term. If you see first, second, third, fourth. So a is 3, first term is 3, and the difference, you want to know the fourth term, and the difference is minus 2. That means 3 plus 3 into minus 2 is minus 6, which is minus 3. Similarly, sum, you can use this formula to find first 3 or first 4 series terms. Now we'll quickly jump on to GP or geometric progression. Right? It's the same, but whose ratio of consecutive terms in a series remains constant. Ratio of consecutive terms is constant. What is GP? Ratio of consecutive terms is constant. Let's take an example. 5, 5, 10, 20, 40, 80. So first term is 5. Okay. Then ratio is, if you see, 10 by 5 or 20 by 10 or 40 by 20 consecutive terms, it's 2. The ratio is 2. Okay. So nth term would be, and sum of n terms. These two we have to understand. The nth term would be a into r power n minus 1. You can try this out, how we substituted for AP. And sum of n terms would be a into r power n minus 1 by r minus 1, where r is not equal to 1. R is not equal to 1. Yeah, this is pretty much about AP and GP. Without wasting our time, we will see, one important concept, how to compare algorithms. Come on. How do you compare algorithms? How do you say whose algorithm is, good? Right? Whose algorithm is good? Okay, we were talking something about execution time from the beginning. We tried, reducing this execution time also, right? But do you think it's the only way to compare an algorithm? Let's find out. There are two friends, okay, or there are two developers. I would say dev 1, developer 2. Okay, clear. Let's say you have two developers. Developer 1 wrote some code which executed in 15 seconds. Developer 2 wrote some code which executed in 10 seconds. So okay, let me give green for this stage. Whose algorithm is optimized? Right. I would say developer 2. Developer 1, no. But if I say developer 2 is using Windows and developer 1 is using MacBook, some Pro. It's not fair. Even developer 1 should use MacBook Pro. You argue with me. Okay. Right. And no offense, I'm just comparing some versions. And the execution time comes to, let's say, 7 seconds. But he also executed in MacBook Pro. The execution time is 10 seconds. So whose code is optimized now? Execution time is less. So I would say dev 1 and we'll reject dev 2. Right. Now what I say, developer 1 is using some programming language called, let me use blue. Developer 1 is using some programming language called C++. But developer 2 using Python. C++ has faster execution time than Python because Python uses interpreter. Again, you say this is not fair. Let the developer 2 use C++ only. After he changed it to C++, it is 5 seconds now. But still my developer 1 is 7 seconds. Right? So again I vote for developer 2 and I reject developer 1. Right? So what is the conclusion here? What is the conclusion? The conclusion I would draw is, right, simply, execution time is not the current way of comparing two algorithms. It depends on various of factors like language you are using, hardware you are using, OS you are using, right, or any other climatic conditions. Let's say one of the developer is working from home and it's too hot at his home, its system is running, it is not running in proper cooling pad, it's already doing some other operations. We do not expect the developer code to execute fast. Right. So execution time is not a single correct way. It's not the correct way actually to compare any algorithms. Then what? Right, you are right. It's iterations. So I would say instead of comparing on execution time, you can say number of iterations is correct way to compare two algorithms. So we discussed factors, then we saw prime, we have seen the execution time, we have seen the optimization we made from the observations, then we have seen some range concepts, we also covered AP, GP, and we have seen comparison of algorithms. in general we have seen how iterations are actually helping us, to compare any algorithms or any compare any code, which actually help you to optimize the brute force approach. Yeah, that's about introduction to problem solving. In the next lecture we will discuss about, clearly we'll discuss about the time complexity and the approaches we have. Thank you all, thank you for your time. Please revise these concepts and go through some documentation, then only jump into next lecture.